Thank you. Welcome, good morning, guten Morgen. So I was thinking when you were talking about defragmenting the room, and I see some fragmented places. So how many of you remember running defrag on like an MS-DOS system? Okay, well, about half of you. So now we're busy getting to know each other. I have another question for you. So how many of you do not speak German? That's quite a lot. Okay, so for those who don't speak German, bear with me for 30 seconds. For those who do speak German, this might be the funniest 30 seconds of this talk. Also, obwohl ich ein bisschen Deutsch spreche, will ich meinen Vortrag am besten nicht auf Deutsch machen, weil ich hier nicht 3/4 Stunde reden kann und es Ihnen zum Lachen oder Schreien anfängt. Also, I will better continue in English. So this talk is about a hobby project. So a project that you do because you like it, because it's fun, not because it's for work or because somebody pays you for it. So how many of you have hobby projects every now and then? Okay, so I do not build self-driving cars for a living, which I think is a good thing because the world would be better off with me not building self-driving cars. But we did this as a hobby project. So will you learn something practical here for your day job? Maybe. Will it be fun? Well, it better be then, right? So my name is Bert Schrijver, and I am going to talk about a project that Tim, a colleague of mine, and I did. And with these type of talks, typically the tension builds up all the way to the end, and then you get a spectacular demo at the end. So I'm going to spin things right around, and we're going to start with the demo right away. I couldn't bring our car here because it turns out that if you take a device with batteries and electronics and wires in a plane, airport security tends not to like you doing this. But I have a recording from an earlier instance of this talk. Start with the accelerating demo right away. And I must say that this is the scariest demo I've ever done. Because typically when I demo stuff, my hands are on the keyboard and I can control what's going on. And in this case, I can't touch the keyboard because the car should drive itself, right? So we have the car up front here. What you're seeing on screen is our web interface where we can control it. We'll talk all about this later. And the objective now is that I will start the car. It should drive itself, stay between the white lines, and then stop when it's not seeing any lines anymore.
So if everyone will cross their fingers now, right? See if it works.
If you're up front, I would advise you to lift up your legs. Because we have, we have an idea what's going to happen, but unexpected things happen all the time. So let's see when we're connected. Here we go. Yeah. we were sweating it a little. We were sweating it a little because I'm not sure. I don't think you can see it on the screen. But we had tested or set up at our office, which has a nice, clear gray floor. And then we went to the cinema venue, and as you might see, there are all these small white dots on the floor. And it turns out that our line detection algorithm was really, really good at detecting lots and lots and lots and lots of little lines on the floor. So we had like 3 minutes to tweak our algorithm to an acceptable way of working. Well, basically, the lesson learned here that if you are trying to make something of the world around you purely based on vision, so on cameras, then lighting conditions like brightness, contrast, and stuff is extremely important. So that's where definitely the weak spot in our solution is, but also maybe the weak spot in some of the more commercial solutions is there. So as I said, my name is Bert Jan. I work at OpenValue. We have a couple of offices in the Netherlands and one in Munich. I am reachable on Twitter at @BSchrijver. You can find my slides there and some ramblings about software and more. I typically present this talk together with Tim, but as you can see, Tim is not amongst us today. Between you and me, Tim is the smart guy from the two of us. So if you see anything in the next 40 minutes that you think, wow, that's really smart, then probably Tim did this. If you see anything in the next 40 minutes and you think, wow, that's really pragmatic, then it's probably me. But I think it's a good combination. So how did this all start? Do Tim and I build self-driving cars for a living? No, not really. It started out as we wanted to set ourselves a challenge. So with a couple of colleagues and a couple of other companies, we formed a challenge. And the challenge was to make a small car self-driving with very limited budget and hardware. So the rules, we had 4 teams. Each team gets a remote-controlled car kit. So it's basically a frame with an engine, a steering servo, a battery on there. Basically everything you need to get a remote-controlled car, except for the receiver. And we got a fixed budget of 150 euros to buy electronics to make it self-driving. So the plan was to do 3 races. The first one, a drag race, so straight trip, drive for 50 meters, stop in a stopping zone. The second one, the same one, but then with corners. And the third one, multiple cars on the same track. So we only made it into race 2, and then we lost some of the teams on the way. But still, it was a fun a challenge to set ourselves. So we started out with, as I said, a basic RC car frame. So what does a car have? It has wheels. It has a steering servo that can steer the wheels. It has a battery. It has an engine. And then typically you plug in a wireless receiver, and then you have a remote control that communicates to the receiver, and the receiver controls the car. We don't have that. So it's a basic car frame. And you can pick this up for somewhat 100, 150 euros, I think. So then we needed to put a brain on there. So we chose to add a Raspberry Pi. Why? Because every hobby project gets cooler if you throw in a couple of Raspberry Pis, right? And also because, well, we had alternatives like using Arduino, but the Raspberry Pi, you can easily run Linux on there, run a Wi-Fi access point on there, so it was an easy platform for us to run on. Relatively powerful and relatively low power in terms of energy consumption. So we needed to power it. Raspberry Pi typically takes 5 volts over USB. So we got this thing from, I don't know, some Chinese site that will convert the 7 volts from the battery to 5 volts for the Pi. So we could power the Pi from the car battery. Then we needed to run some software on there. So we decided to go for at least Java, because we were Java developers. And we chose to use Vertex. So how many of you have heard of Vertex before? Okay, well, about 25%. So Vertex is a fairly general purpose toolkit for building reactive applications on the JVM. It is event-driven and non-blocking. It's fairly lightweight in terms of memory consumption, in terms of size on disk. It's polyglot, so with Vertex you can build applications in Java, Kotlin, Scala, Python, JavaScript, I don't know, maybe even PHP. And the cool thing is it has a distributed event bus. So if you build an application consisting of multiple components, and they can run everywhere on the network, the distributed event bus automatically changes everything together, and you can easily send messages between the different components. And this is useful for us, because then we can run some parts on the Pi and some parts on our laptop. You can even take this event bus all the way through to the browser. So events you're generating in your browser can automatically get delivered to your different parts of your network. If you want to know more about Vertex, I did a talk on it once about how we use it as a customer. It's up on YouTube. You cannot click this link, but you can once I share the slides. So then we needed to hook the car up to the Pi. So a Raspberry Pi has these types of ports here, lots of pins, where you can connect stuff to. So what we did was take the wires from the steering servo, which makes the car steer, and take the wires from the speed controller. And the speed controller basically regulates the amount of current that is going from the battery to the engine. So for example, 100% is full power ahead. 100% voltage reversed is full speed reverse. And anything in between is less than full speed. So we hooked this up, and then we needed to put some signal on there. So the GPIO ports are, well, fairly general purpose I/O ports. You can connect devices to there, sensors, lights, and they typically either have 5 volts or 3 volts, or there's data pins, and you can control what happens with the data pins. So in order to use these pins to talk to the speed controller and the servo, we needed to find out, how do you control these? And it turns out that this is PWM, which stands for pulse width modulation. And this is a way of sending data over these GPIO pins. So you're sending pulses of variable width, and you can basically use this to send numbers. For example, a number from 0 between 255 can mean anything between full speed reverse to full speed forward. So we use the utility called Servo Blaster for this. It's open source. You can run it on your Pi. Then you basically get a Linux device where you can write data to. For example, you can say echo 100 greater than 3 to def Servo Blaster. And this will mean that it will send to servo 3, it will send the value 100. So if you want to do any hobby projects with servos, this is a real easy way to start. And fairly quickly, we noticed that safety was important when you're making a car drive itself. So our first prototype was basically everything I've told now. So we have the car, the Pi is on there, it has it's running Linux, it has a Wi-Fi access point, and it has a Linux device where it can echo commands to. So the first prototype was I log in over SSH to the Pi, and I type echo 3 is 100 greater than dev server blaster, and the wheels turn. Nice. Okay, so we have to try to fiddle to set the wheel straight. Echo, I don't know, 4 is 255 dev server blaster. Car starts bursting away at full speed. We're running, but it can go like 80 kilometers an hour, so no way to catch it. Runs into a wall, goes out of reach of Wi-Fi, crashes, etc. So safety is important. So the first thing we did when we were building this with Java is build a heartbeat. So car should receive a heartbeat signal from the laptop. We use it to control, I think, every 100 milliseconds. And once it had missed 2 or 3 of these heartbeats, it will shut down. So if the control software crashes, if the network gets congested, if the Wi-Fi connection drops, the car shuts down. And this has saved us many times. And then we eventually wanted to drive it itself, so it needed some sort of camera. So we took a Raspberry Pi camera you can pick up for somewhat around 30 euros, put it on there, and then we used the Raspberry Pi Cam web interface, which surprisingly is a web interface for the Raspberry Pi camera to configure it and to stream video. So we could open, I think, an MPEG-4 stream from the device and stream video to our laptop. And you can also use it to configure video settings, so stuff like brightness, contrast, frame rate, the image size or the resolution. And then we were somewhat ready for the road. So what you see here is, well, basically the car. We found out that it helped if we put the camera a bit higher up so that it can look closer up front of the car. We added a fisheye lens, which is basically one of these lenses that you can put on your mobile phone and then you get a wider view. So we use this to see as close as possible in front of the car. There's a big Wi-Fi antenna on there to get some more range, and that's basically it. We were now ready to drive. So it kind of looked like this. You can forget the images on the right for now, but we have like the image from the car here. There's some control info here, and then here's some debug info from all the events that are being sent on the Vertex event bus. And now we could drive the car by using the keyboard in the web browser. So if you would press a key, the Vertex event bus would send a command to the control software that's running on the car. So what do we have now? Basically a normal remote controlled car with a $3,000 controller. So nothing special yet, right? So now it's time to learn the car to drive itself. So we needed something to turn camera image into steering commands, basically. And for this we chose OpenCV. How many of you have known of OpenCV? Okay, about 1/3, I'd say. Well, it is an open source computer vision and image processing software. And it's implemented in C++. It can even run, I think if you use CUDA on the graphic card of your Mac. And it has Java interfaces that you can call via JNI. So you have a Java interface, but it's actually executing native code that calls C++ code over JNI. And has lots of fairly optimized algorithms that can do basic computer vision processing tasks. It's fairly widely used, and there are lots of resources available. So lots of demos, examples we could get. So this seemed like a reasonable choice, and we still think so. So then it's time to share our image pipeline. So an image pipeline is basically a sequence of steps where you apply transformations to an image. So we started with the raw image from the camera. So you can see we're not using the entire image, but we're using like a specific field of view because this allows us to process less pixels than if we would use the entire image. If we only need the bottom part, then we can throw away the top part. This will speed up in processing time. So the first step is edge detection. And a widely used algorithm for this is Kenny. It's been around for a while already. They're really optimized implementations in OpenCV, so this goes really, really fast. So we take the image, we apply Kenny edge detection, then you basically get this. It detects edges here, and then it detects an edge here, which I think is a chair or a box that's on the floor, but this is still fairly good. So we then apply a line transform, a U line transform to the image, and this gives us the green lines that you see here and here. So there were 2 versions of the U line transform algorithm. There was the regular one, and there was the probabilistic one. And then we read somewhere that the probabilistic one was better, so we used that one. So there's no like real big choices made here. And then we applied, so now we have like, we're plotting these lines ourselves on the image. So we have basically vectors that represent these lines, and as debug info, we're plotting the lines on the image. So then we could like take the average of the outer boundary and the inner boundary, and that's what you see here. So we are averaging the lines, and we can also extrapolate a little. So if you see that we have a line here that's going all the way here, and it stops here, then we can safely assume that it will continue here, but there's something on top of the line. And once we have the lines on the sides of the road, and we know that the camera is in the middle of the car, we can determine the center of the road and also where our position on the road is. And in our first prototype, we were mainly steering the car based on the angle the car was making on the road. So if we're angled to the left of the road, then we need to steer right. If we're angled to the right of the road, we need to steer left. And Tim had been saying from the start that we shouldn't only look at the angle, but I didn't listen to Tim, so this was our first implementation. So it's time to show you some code. So how do you implement this in Java? Well, you're probably going to be disappointed a little by what I'm going to show you. So this is the class that's doing lane detection for us. So the first we're doing is getting a region of interest, which is mainly throwing away the parts of the image that we don't like. We're determining a viewport from this, and then we have a line extractor. And the line extractor is using Kenny for edge detection and the U-lines detector for detecting lines. So let's go to the Kenny edge detector. We have some config values here, some thresholds, the size of the aperture. And then basically everything we're doing is this, imageproc.kenny, and then feed the image in there and the thresholds. So how is this implemented? This is implemented as Kenny2. And what is Kenny2? This is a native method. So here we're jumping to the C++ implementation. So how about the probabilistic U-lines line detector? Also some config values, and then here it's again a one-line call to imageproc.ulinesp. So how is this implemented? You're guessing this already, it's also a native call. So this is also calling the optimized implementation in the C algorithm. So yeah, nothing fancy here, but it also shows you how easy it is to do this with a framework like OpenCV. You only need a couple of lines of code, and then you have an optimized implementation of Kenny edge detection of probabilistic U-line detection. So every project needs an architecture, right? We work as software developers and software architects, so we need to make an architecture for our system. So this is what we came up with after a night of thinking and maybe consuming some beverages. So do these names mean anything to you? Do you recognize these names? The Dukes of Hazzard, yes. So our team was called the Dukes of Hazzard, so we decided to name all the components in our system after characters in the Dukes of Hazzard show. This turns out to be not so optimal, because the most accessed file in our repository is the README file, which describes which component does that. So typically you want to work on a system. Oh, I want to change, I don't know, the intermediate CV, OpenCV images. We go to the README, which is, oh, this is Daisy. Oh, we need to go to Daisy. So I wouldn't advise doing this, but still, you know, it's for the example, it's nice. So everything you're seeing on the right side is running on the car, on the Pi. So this is a JVM that's running there, that is running Vertex, that is running a couple of Vertex modules that are connected to the event bus. Everything is running on the left, is running on the laptop. And the nice thing is that it's fairly easy to take a component that runs on a laptop and then run it on the car, because it doesn't matter whether you're sending messages within one JVM or over the network to other JVMs. Vertex ties this all nicely together. So it all starts with the image feed. And the image feed is processed by Daisy, which runs on the laptop, and it sends debug images to Roscoe, and this basically allows us to get an idea of the lines that we're detecting. So Daisy sends the angle and the distance we are from the sides of the road to Luke. And Luke was always the leader of the gang. So Luke is now sending steering and speed instructions, like go left, go right, go faster, stop, to Bo. So Bo was the one who drive the car. And then Bo is sending commands to Servo Blaster, which is in turn instructing the steering servo and the speed controller to drive. And Servo Blaster is also turning the LED, the safety LED on and off. So we have the LED on there. Once the LED is burning, then we know that we're receiving the heartbeat signal. Then we have Boss Hawk, who I think was one of the law enforcement officers. This is the user interface. So he's sending manual inputs to Bo, and he's sending the heartbeat to Flash, which is the heartbeat controller. So what we're seeing is that on the car, only the basic stuff is running. So there's a small module that's interpreting messages from the Vertex event bus and sending them to Servo Blaster. And there's the safety module that's receiving and checking the heartbeat and shutting down when they're gone. And basically all the image processing is run on a laptop, which is nice because it's fast and you have quick development cycles. You can easily change stuff on your laptop. But we also have an image feed, so the stream of video, to go over the network to the laptop. So in the end, it would be better if we would run everything on the car, but probably we would need some more powerful hardware to be able to do this. So we expect to have built a, well, let's say a fully working self-driving vehicle, for example, like this Tesla. Who agrees that it will probably be as good as a Tesla? Thanks for the support. Well, in reality, it was more like this. So we had some self-driving capabilities, but yeah, well, on a good day, it worked sometimes. Let's put it like this. So it's time for some videos. This is a video from the kitchen where we actually did our first integration test. So this is what we learned if you're like building electronics. Testing is a lot harder because you need room to test a car. We didn't have any way to run a simulation. So here we're testing like the first full circle integration test. The car is looking at the starting light. Once this light goes off, it should drive, stay within the lines, and stop in the stopping zone on the left. So let's see. All right. Yeah, so this was a huge success for us. And here are 3 grown men in the kitchen getting all excited over a toy car that's doing something. The joys of life. So here we are practicing in the big factory hall in our office. And here we have a little bit more room to experiment. So I would say this was pretty good, but you might have seen the car swerving a little as it came to the end. So somebody in a previous edition of this talk called this autonomous drunk driving, and I think that adequately describes what we're doing. What you're seeing here is a kind of overcompensation. So we're steering based on the angle of the road. Oh, we're going left, so we need to steer right, but we steer a bit too far, and then we need to correct again. So the car was swerving more and more and more and more. So we tried to apply some damping to this, but still, we couldn't drive for like 60, 70 meters because then it would swerve out of the area. And this was all because I was still steering based on the angle, and Tim had said before that we need to do more than steering just based on the angle. So we were practicing in our office, and our office is in a huge factory hall in Utrecht in the Netherlands, and there regularly are events there. And this was, I think, the Baby Expo, where you can go buy new baby rooms and strollers and everything for your soon-to-be newborn child. We were practicing here on the side, and for some reason the car decided to make a left turn and go straight into the exposition. And then people were running and shouting, they're like, "Ah, it's a drone, get it away from here." Or, "No, it's okay, it's just a car." And then we were thinking, like, what happened? And we were kind of like giving this some thought. And then probably what happened is it kind of got lost somewhere here, and then steered a little to the left, and then thought, "Oh wow, there's 2 nice white lines in here. That's the road. I'm saved." And I drove in there, and then got stuck a little. And then we noticed that we really needed a way to debug this, other than just looking at the car driving and seeing what happened. We haven't done this yet, but we still need it. So here we're practicing inside our office where we're experimenting with a bit more difficult lighting conditions, because what we're seeing is that stuff like light and dark and reflection can have a big impact on purely the ability to do good edge detection. If we cannot do edge detection, we cannot do everything, and the car will probably crash. And it stops at the most important part of the office, the bar, obviously. So does it go this well every time? I think this was the 5th or 6th take of the video I was taking. So here's one of the earlier takes. Yeah, so what happened here? We didn't really know, until somebody pointed us out that, well, the car's actually nicely driving between one white line and another white line in the reflection here. So this is also a risk. It might detect lines that are not there because of reflections that are in there. So then it was time to race. So initially 4 teams had signed up for the race. Our car was driving pretty okay. We're practicing all day. Another team was also driving pretty much okay. One team, the car didn't drive at all, and there was one team that had built a car. Are there any front-end developers in here? Okay, you might. I apologize for what I'm going to say, but the front-enders had built a car, and it looked awesome. It was really fast. It had flashy lights. The wheels were great, but it couldn't drive itself. And they actually had quite a smart plan. So their plan was to put the car in the starting position, let it drive straight, measure how long it would take to the stopping zone, and then after like 16.2315 seconds, cut off the engine. So what happened, it started, it took a right turn, and we've never seen that car again. So there were 2 teams left, and we were practicing during the day, and our car was doing pretty much all right. The other was a bit better, because they had a better steering algorithm. So we're thinking, okay, we'll be 1st place or 2nd place. And then for some reason, we had decided that we would do the race in the evening. And I'm not sure about Berlin, but in the Netherlands it gets pretty dark in the evening. So the cars couldn't see anything. So as you can see in the picture, we drove in some of our own cars, put some lights on there, but the lighting conditions were pretty horrible. We had like bright light in one position, and then it was dark in another position, and we tried to tweak like the lighting of the camera a little, but we basically couldn't get it right for the entire track. So we started, the cars drove off, the other was faster, ours was going a bit slower because we wanted to give the camera as much time as possible to see the world around it. So the other one was going faster, and halfway it switched lanes, it went to our lane, then it went all the way to the end, and it stopped perfectly in the stopping zone. So we're like, oh crap, that was pretty good. And then our car drove just a little further than the other car in its own lane, and then it swerved off into the dark. So we were like, okay, the other one was clearly better. But the rules clearly stated that the car that would drove the furthest in its own lane would win. So yes, we won, but I must admit that the other car was actually performing a lot better than ours. But it was fun to do this. It was a fun event. So then we started to work on improving it a little, and I finally listened to Tim saying do not steer purely based on the angle, because if you're driving a car yourself, you're not steering on where you are. You're not looking like at the lines of the road like 1 meter ahead and then continuously steering, but you're looking ahead. You're steering like where you need to go. So then we started to detect like where is the horizon of the road going. So where do the left lane and right lane cross, and try to steer there. And this immediately worked a lot better. So the ping pong ball is just there for reference. But you can see that's already trying to navigate corners a little, and it's actually ending up pretty near perfect in the middle of the road in the end. So now we're just looking as far ahead as possible and trying to steer there. So this saves us from a lot of corrections and a lot of oversteering. And then the final version, we made the field of view even smaller. So if you look closely at the image, you can see that the green and the red line and the blue line are only like taking a small section of the road ahead. And then we're currently moving this and reevaluating how we should steer. And with this change, it actually was able to steer through corners pretty okay. We've also added lots of like sliders to tweak the parameters of the algorithms, which also helps to make it better. So let's take a look at how this went. Slowing down because the battery is almost empty. So that was pretty good, right? And mind you that this is just a rule-based system, so there's no AI or neural networks involved yet. I must admit that the initial laps the car drove here, it would sometimes miss the road, cut some corners, so we might have adjusted the road a little to suit the capabilities of the car a bit better. For example, you saw that this white line was exactly aligned with the shade that's produced by the pool table. Well, that's not a coincidence. So we cheated a little, but still, it produced a nice video. So let's compare this to how cars in the real world are doing this. We have a couple of like big competitors. So obviously Tesla is doing a lot of this space, and there's Waymo, the self-driving car unit from Google, that's doing pretty good. So there are currently two approaches that you can take to self-driving cars, and they all have like a different level of autonomy that cars have. So level 0, you can do anything at all. Level 1, you can do one thing, like braking instead of in an emergency. Level 2, you have at least 2 automated features, for example, adaptive cruise control and lane assist. There are already quite a lot of cars that have this. Level 3, cars can handle dynamic driving, but may still need manual intervention. Arguably, Tesla would be at level 2 or 3. I think they say they're at 3, but they might be at 2. Then there's level 4, officially driverless cars. Some of the cars that are driving in I think Arizona are conform to this level, and then level 5, they can operate entirely on their own presence without any driver. I'm not sure if any cars really adhere to this level yet. Obviously, the marketing department of the self-driving car companies want you to believe this. So there are 2 strategies. There's the expensive strategy and the cheaper strategy. Well, in terms of hardware. So what Waymo, for example, is doing is they are making use of fairly expensive sensors, mainly a LiDAR, which is a laser radar. So this is mounted on top here and here, and a LiDAR continuously sends laser beams and records the responses, basically like a radar or a sonar, but then with laser, and uses this to plot a 3D image of the world around it. Obviously, there's cameras and radar in there too, but LiDAR is like the most important part. So how would a car view the world? Well, maybe something like this. It can measure distances. And the advantage of using a LiDAR is that it's not susceptible to lighting conditions or fog or something, because laser will shoot through fog, so that this can work fine. You can also buy like pre-mapped 3D environments like this from companies like TomTom that can help you in getting a better view of the road. Then there's the cheap hardware approach. That's the one that Tesla uses. So they mainly use cameras and a radar and ultrasonics, but mainly cameras. So there are lots of cameras installed in every Tesla, and then they use a computer vision pipeline and a neural network to turn these images into a view of the world around it and convert it to steering commands. And I would say that Tesla has one of the best cards in the game to become really good at this, because they've been gathering data from these cameras and the road for all the cars that have been driving around there for years already. So they have a really good data set to train their algorithms, to train their networks to make cars really self-drivable. On the other hand, a LiDAR gives you a lot more information than just cameras do. So I think both approaches have advantages. I think on consumer cars, we won't be seeing LiDARs anytime soon, because I think they're still around somewhat like 100K euros or something to get one. So this is how a Tesla might view the road. It's detecting lines, detecting cars. But wait, that's an interesting Tesla logo. This is actually a Honda. And this is the Honda from George Hotz. George Hotz became famous years ago because he was one of the first to jailbreak the iPhone, one of the first to hack the PlayStation. And at the time, George Hotz invited a journalist at his home, and he said, like, would you like to see my self-driving car? I built it myself. Sure, they went in, and they saw something like this, and it went all fine. And then the journalist asked, like, okay, so how many test drives have you done with this car? And then George said, smiling, this was the first. But it went pretty well. And then so he did this in the States, and the American government got note of this, and they said, well, I think it's not a good idea that civilians are making self-driving cars, so you cannot do this. So George said, that's fine, I'll found my company, and he's now, I think the company is called comma.ai, where he's producing software to do this. So you can actually, with fairly cheap hardware, just a phone, and you need, I think, a Bluetooth ODB plug that plugs into your car, and here is using the adaptive cruise control and lane assist of his Honda to automatically steer the car. And most of it is open source. I think only the image processing pipeline you need to pay for, but still, it's a nice experiment. So obviously, safety is important when you're having a car that drives itself. So there are a couple of safety measures. The first is geographic area limitation. For example, there are cars that are only allowed to drive in Arizona or in Texas because the roads are good and the weather is always good. So it's a lot easier to get a good view of the world around you. Strictly defined conditions. You can only drive when it's not raining, when it's sunny, when you have good view. Obviously redundancy, just like in planes. You don't want your car to crash because one of the controlling computers is installing a Windows update, for example. Multiple sensors, so you want to have assurance from multiple ways of input that your image of the world is actually the right one. So if one sensor fails, and you can detect this failure by having 3 other sensors that are saying the same thing, which is different from this one, this can help you. Obviously, isolating control systems. So make sure that if somebody gets access to your in-car entertainment system, they cannot hop via your local network to your car control system, where they could maybe disable the brakes when they hack your car over the internet. And obviously, human intervention fallback. So somebody should still be present to take the wheel if something goes wrong. And this mainly has legal reasons. So in a Tesla, you're not allowed to let your steering wheel free, because if it crashes, they want you to be liable for the crash, which I understand from a company's perspective. So lots of these cars are, and other systems are using AI for computer vision. But AI for computer vision, this is a system that's fairly widely used and for detecting persons. So it is detecting the person on the left, but it's not detecting the person on the right, who clearly is a person, I would say. He has this strange patch attached to him with, I don't know, I think people and some umbrellas. And he's saying, look, I got this patch here, but why are you not detecting me? People detecting AI. Hello, I'm here. I'm a real person. I can wave. And then what happens if he takes away the patch? He is immediately detected as a person. So probably this system has never seen like somebody with a patch attached to his belly, which I can imagine. But you can see that it's fairly easy to fool. So imagine that you are this person, and that a Tesla is approaching you, and you're walking across the street, and you're holding up a box with toys or a puzzle. You're walking like this. And the Tesla thinks, no, you're not a person. I won't brake for you. So these systems are still fairly easy to fool, and that's something you need to take into account, especially when you're just using computer vision. Obviously, you would combine this with, for example, a radar or something. So ethics. I'm going to skip this comic, but it's basically saying, in a crash, I should preserve self-driving cars because there are not that many cars and there are lots of humans. But that's just how a computer might think. So let's do a small experiment. This is the Moral Machine from MIT. This car is driving here, and the brakes are gone. It cannot go outside the road because there are concrete barriers. It can either go straight and kill 3 dogs, or it can swerve left, evading the dogs, and kill 3 cats. How many of you would save the cats? How many of you would save the dogs? More dog people in here. I'm going for dogs too. Do you know the amount of damage a cat would do to the grill of your car? That's. But on a bit more serious note, what if this were people? What if you're driving in your car with your family, and the car is in self-driving mode? There are concrete barriers left and right. There's a concrete barrier on the road. And there's another family crossing the road in front of you. and your car needs to make a decision. You're too late to switch it off. It's in self-driving mode. Your brakes are done, you cannot drive, so you have two options. Drive straight through and kill the family that's crossing the road, or swerve to the left, smash into the concrete barrier, and kill your own family. By a show of hands, who would drive straight through, saving your own family in the car? Who would swerve, kill your own family, and save the family on the street? Who thinks this is an impossible choice to make? Yes, obviously. But cars will need to make choices like this. And would you get in a car that's programmed or has learned to sacrifice the family inside it? No, I wouldn't. Would you go into a car that was programmed to sacrifice a family on the street? I would also not want to do this. But there are rules. I think this was actually from the German government. So when a situation is unavoidable, the protection of human life enjoys top priority. Okay, that seems reasonable, right? You're not going to save your car if you can protect human life. But the next one, in an unavoidable accident, you cannot make distinction based on personal features, so age, gender. This is prohibited. And this is where it becomes a bit more shady, because what if you can only swerve left and right? Left of the road, there are 3 young children. Right of the road, there are 3 elderly people. Would it be more reasonable to save the children or not? I don't know, that's also an impossible choice. But what if there are 3 children and 5 elderly people? Would it make more sense to save the elderly people or not? These are hard and mainly impossible choices to make. So this is something that you need to give a lot of thought. And thinking a bit more about ethics, there also was a emissions scandal, I think with the Volkswagen Audi group, where cars were programmed to behave differently in emission tests. And the developers that built this were told to do so by their managers, by their bosses. But some of the developers who built this are now in trial for building the software that's evading like emission laws. So you as a developer, be aware that you can go to jail for doing something unethical that your boss tells you to do. So always think twice if what you're doing is in any sense an ethical option to do. So back to the fun world of hobby projects. Stuff that we would like to work on in the future if we ever find time. Well, the detection and navigating of curved lanes obviously needs to improve. And we can optimize a lot there. And I think one of the most important things we can do is find a way to automatically recalibrate brightness, contrast, the parameters of the OpenCV algorithms, basically by cycling 2 different options and seeing which one gives us the best image. We need some way to replay and debug what happened. Why did the car drive into the expo area? We have no idea. We could control the servos directly from Java instead of saying system but get runtime but execute and then echo this to pipe that. You can maybe imagine which of the 2 of us built this. And I think one of the next steps would be to move away from a rule-based system and move to, for example, a neural network where we train the car based on camera inputs, sensor inputs, and then learn it how to steer. But this would involve us in training the car for probably hundreds or thousands of hours. So this also takes a lot of time. Maybe we could use a simulation here, but this will be like the next big step. And we would like to optimize for running everything on the car, because now we're running all the important parts on the laptop, and we could also run the image pipeline on the car, for example, by using the Movidius compute stick by Intel, which is basically a neural network on a chip. So, we may have some seconds for questions, but first I want to tell you a couple of things. Everything I showed you is up on GitHub, github.com/rcjugs. There's actually a contributor who's currently working on this project and using it for software architecture trainings. In the same room, after my talk, my friend Mark West is going to talk about how he used the Raspberry Pi and the AWS cloud to create a security system for his home. So if you're into like hobby projects and IoT, definitely stay in. Thanks a lot for your time. I'll publish my slides on Twitter. I'll be around for the next few days, so feel free to reach out. Thank you.